Hi guys. We have a lot to get through today, so we're going to get started here. Because we're covering all the small things in the solar system today. So what I mean by that are asteroids, comets, Pluto, maybe meteorites, things like that. But yeah, we're going to get through a lot of different things. This is a pretty picture of a comet. A comet is, they come in, they're icy balls that come in from the edge of the solar system in the Oort cloud. And when they get close to the sun, they get these nice tails. We'll talk about that more today. And they get very photographically pretty. I think that's fair to say. Okay, so starting off, asteroids. So asteroids are primarily bits of rock that live in the inner solar system, and most of them live in this area in between Mars and Jupiter called the asteroid belt. The asteroid belt, to be clear, is very empty. I know in sci-fi, video games, things like that, it's usually a bunch of rocks and you have to like squeeze through them, this and that. I'm sure by this point in this class, you appreciate that space is really, really big. And the same as in the asteroid belt, like you might see one or two nearby as you pass, but it's not really a huge field that's you're going to, run into another rock or something like that. We have some other asteroid groups as well that are smaller. The most notable ones are in Jupiter's orbit. About a third ahead and a third behind Jupiter are what are called the Trojans collectively. So the Trojan asteroids, and there's also the Greeks. It's the Trojan War is the idea. So you have swarms that are basically captured asteroids that orbit before and after Jupiter in kind of resonances of its orbit. But really, the majority of all the asteroids that you're ever going to hear about are in the asteroid belt. You have some that will come closer. So, we do keep an eye out for what are called the near-Earth asteroids, or NEOs, sometimes they're called. But they're much, much less than the rest of them. So yeah, most asteroids are in that asteroid belt between Mars and Jupiter. If we look, so this here is distance from the sun on the x-axis in astronomical units and number of asteroids. You can see that, you have many, many asteroids. You do have gaps in the asteroid belt if we're just looking at them. And this has to do with these gaps here is what I'm talking about. They're called Kirkwood gaps, and they're basically caused by gravitational resonance with Jupiter. So if you were an asteroid and you, for whatever reason, ended up in one of those orbits, eventually you're going to interact with Jupiter. Jupiter is a much, much bigger asteroid. It's going to nudge you into another orbit if you find yourself there. We currently know of about 700,000 asteroids, and I'm talking anything that's like some of them are, maybe just a couple of feet in size across. Some are, the biggest asteroid series is actually a dwarf planet, several hundred kilometers across. But most of them are not terribly big, maybe more like house size, couple kilometers across, those sorts of things. They're very, very small, as I said, compared to planets. We're not sure of how many asteroids there are, but we think we probably haven't even found half of them yet, because there's just a lot of them and they're not very big, so that means they're not very bright. So finding them can be a bit more problematic. If anybody's curious about, if asteroids can come in and hit us on Earth, we could think there's maybe about 40,000 that come and cross Earth's orbit. So those near-Earth asteroids, near-Earth objects, compared to the million-ish asteroids out in the asteroid belt that are never really bothering anyone. Asteroids come in a few different flavors. So the main flavors are called the C-type, the S-type, and the M-type. So C-type means carbon-heavy rocks or carbonaceous. Let's see. Yeah, so Ceres here, which is the biggest asteroid, is in fact a dwarf planet, is an example of one of these carbonaceous C-type asteroids. On the other hand, the second kind we have is called the S-type. They're silicate or silicon plus oxygen asteroids. They're mainly famous because they actually are very highly reflective. They're kind of easy to spot compared to the other asteroids. So Eros, this tiny guy here, is an example of one of those. Vesta, I think, is also in that category. And finally, M-type. M-type basically means that they're metallic, so made of metals. So you're not really having these carbon, silicon, oxygen things. You're having nickel and iron. So Psyche which is an example of a metal asteroid. So I know that a lot of business majors are enrolled in this class. Some people say if you could get one of these close enough to Earth, I mean, one of these, they're so big because they're, several kilometers across. It's like trillions of dollars of rare earth metals and metals in general. So, start your business plan if you really want something pie in the sky, asteroid mining. Some people have actually been thinking about this and how to do it. So we have all these different asteroids. Where do they come from? So the first thing about asteroids is we think they've been, for the most part, well, there's some exceptions, around since the beginning of the solar system. They might even be original material, some of them dating from a little bit before, but the point is they're left over from the early formation of the solar system. They're differentiated, or some of them at least are, so you will have different layers between them. And you're also going to have some collisional products, so broken pieces from other planets earlier that have since broken apart, maybe because of impacts, maybe because of gravitational effects, things like that. So to give you an idea, this is Eros, which I showed you guys on a very, very tiny scale earlier. The craters that we have, they're partially filled in, but it's basically a rock that has been around for 4.5 billion years old if we use crater dating to try to figure out how old it is. Ceres is big enough that it actually is differentiated. We have sent a mission to Ceres called Dawn, and that's how we can kind of see that this is what's happening there. And then those metal asteroids like Psyche, it probably didn't form as a chunk of metal that's been like that ever since. It was probably part of a larger planetesimal, had some sort of rocky core that since broke up, and then that's how you have a metal hunk worth trillions of dollars floating around the solar system. The other thing we can see is asteroids can have families. So these are groups of asteroids. So these are asteroids where if you're looking at the orbits and the compositions, you'll be like, hey, it looks like these are all traveling together, for example. As an example of what this looks like, so if we're looking in distance here on the x-axis, asteroid proper orbital elements is what is on this axis. There's groups. You can kind of see, so Ceres, there's a lot of, there's a thick clump around the values for Ceres, the biggest asteroid. And then we have a few other clumps. Some of them you can note, we don't actually have a main asteroid. We're not 100%. We just think there's a family and we don't know what the original progenitor was. And the idea here, the point of having asteroid families is they kind of tell you that if there's some original formation and then things since broke apart, maybe this is the family that is left over from that initial planetesimal or something like that. That's kind of the idea behind what could maybe be causing these asteroid families. We also see evidence of this if we look at things like the composition and the distance. So if we think of distance from the sun here on the x-axis, and then the percent of the kinds of asteroids we see, it's not uniform in the entire solar system. So this is, out to the orbit of Mars, out past Jupiter. You can see that you have more of those stony ones closer in, those carbonaceous ones further out. Metallic types are kind of more in that asteroid belt region. So this also tells us things about the initial formation of the solar system. If these are leftover pieces from that initial formation, where they end up on this is also part of that. I've been talking a lot, so we're going to have a quick question to see how you guys could think about, these different compositions. So asteroids can be made of rock or ice. So if we have the density of rock is there as an example, density of ice, what do you think could make up an asteroid that has an even lower density than rock and ice on their own? Yeah. So if you had a mix of different things in an asteroid that, and also you just have empty space in that asteroid, you can have asteroids that are very, very low density, definitely not just a hunk of metal or something like that. An example of this is there's a type of asteroid called a rubble pile asteroid. So there is an asteroid called Itokawa, which is a low density rubble pile. This is what it looks like. So it's very, very weakly bound rocks and ice chunks. You'll notice there's no craters on this surface. That tells us it's very young. We think, in fact, it's only about 8 million years old. It's kind of amazing. The reason we think that for this asteroid is there was a Japanese mission. It went took a sample from this asteroid and brought it back to Earth so we could analyze it. It's the first successful sample return mission that we've really had from another celestial body. And what we learned from that is that its dust suggests that it's only 8 million years old. So there's probably some sort of impact that, a lot of small rocks came, and then some of that debris recoalesced, gravitationally was attracted, created a chunk that is now this asteroid. One final thing that I always thought was pretty cool is asteroids can actually also have moons. So this is an asteroid that, kind of looks like a very nice space potato. Its name is Ida. And when the Galileo mission went to Jupiter, they actually discovered just from the imaging that, it actually has a moon, and they named the moon Dactyl. For a sense of scale here, the length of this asteroid is 60 kilometers. The distance between Ida's center and this asteroid is about 80 kilometers. The moon asteroid is about 1 kilometer in diameter or so. So very, very tiny moon compared to most other moons that we really know of. But I thought this was kind of a neat one that, yeah, even asteroids can have moons. Comets. So comets are also small, but they're very different. They originate from a very different place. The way we can tell is they have very large eccentricity orbits, which we've discussed earlier in this class. What this means is they come from very, very far out at the edge of the solar system, well beyond Pluto, in this hypothetical area called the Oort cloud. The second thing to note about comets is most asteroids are actually in the ecliptic of the solar system. They don't, some go up and some go down. For the most part, they appear to be in that disk. That is not the case for comets. They will come from pretty much every direction that you can imagine. To give you an idea of what comet inclinations are like, so if we think of that solar system plane, that ecliptic, and this is the sun in the center, we had Mercury's orbit, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Most of them are, within a couple degrees of that solar system ecliptic. But then comets will come in, as I said, from all directions. These are just the names of some famous comets that we've seen in recent decades. I've seen these two, Hyakutake and Hale-Bopp. They were in the late 1990s. They were bright enough that it was like all over the news, go out and you'll see a comet. They were last great comets is what they were called. So I was a kid and I happened to see them. The location of comets, so very high eccentricity, and they spend most of their time very far from the sun. So you'll remember Kepler's law, which says that equal parts of that orbit have to sweep out different distances. So they spend most of their time very, very far. They are traveling very fast when they're coming in on that inner part of their orbit where they're going around the sun. And they briefly enter the inner, that means they only very briefly enter the inner solar system. Sometimes they only enter once. There's definitely some comets where you see it coming in, it's on an orbit that you're like, okay, that thing is never coming back. We'll discuss that in a little bit. A lot of comets will have, if a comet has an orbit of decades, that's a very short period comet. Hyakutake, for example, this one here. So it was 1996 when it came, and it was in the north. It was very bright. So my dad took us out. I was a 10-year-old kid out to the country to see it. I look up, and then my dad's like, well, the next time it's going to come is 74,000 years from now. And think about me when you see it again. And when you're a 10-year-old kid, that's the first time I kind of realized, like, oh, there's actually things that will last much beyond us in this solar system. So comets are definitely a good example of that. There's billions of comets we estimate out there. Most of them are just hanging out in that Oort cloud, never come in toward us. We know about 4,000 of them currently. So we only know a very short number of them. Only if they come in toward our inner solar system can we really detect them. Because otherwise they're really not very bright, hard to detect, very far out. So composition of comets. Comets are made of a small nucleus that's maybe a couple, or maybe 20 miles across or something like that. So, a Eugene-sized thing. And it's a fluffy aggregate of very loosely bound rocks, dust, and ice. Near the sun, you get sublimation, which is going to release gas and dust from the nucleus into what's called a large coma. So that's kind of the fuzz around a comet. I'll show you guys a picture in a minute and show you guys what this looks like. And as the comet travels, I think most people know this, a coma, some material is going to be left behind, and you're going to have what's a tail behind the comet, which is basically in the direction away from the sun. It has nothing to do with the direction the comet is going. It's usually just always away from the sun. So to give you an idea of what this, so this is actually from a European mission called Philae, which went and landed on a comet 67P Rosetta, or sorry, Rosetta was the mission. It landed on 67P. And it actually successfully landed on the comet, which was kind of amazing. This was 2013 because nobody knew you could do that. And this is what it looked like. It turns out there's like, you can have canyons, you can see there's loose rocks. This is not, it's not actually snowing. These are cosmic rays that are hitting the detector on the instrument. So cosmic rays being those solar particles. There's no protection. There's no atmosphere on this comet. So it makes it look like it's snowy, but it's not. There's also just stars in the background. You can kind of see the Milky Way there for a second as it's going. So it's not that it's snowy or it's the dust or anything like that, but it is pretty spectacular that we have like actual details of what it's like to land on a comet surface like this. So comet tails. This is kind of a very classic comet with two tails. So you have two tails. So that first, the equivalent of what this looks like. So down here in the little bit here, we have that cometary nucleus. Okay, I misspoke earlier. Only 1 to 10 kilometers across. So even smaller than Eugene, like here to downtown, I guess is maybe a comet size. But it has all that vapor. It's going to get very hot as it's going toward the sun. And you're going to have this giant dust tail, which is going to be that material from the coma. The coma is this area around here that kind of makes it bigger, because if this is only 1 kilometer, you're never going to see it. You really are seeing the coma. You see this dust tail going out in this direction, and then we see what's called the ion tail, the second one. So the ion tail is the ionized gas, which is blown back by that solar wind, so those solar particles interacting with it. And then the dust tail is the particles that are left behind in the direction that the comet was traveling. Fun fact, the dust tail is then when you have a meteor shower on Earth, those particles are left, and then Earth's orbit, many, many years later will cross that orbit. So you will get all these little meteorites, and that's what creates the shooting stars in a meteor shower. So that's how those work. So the question for you guys here, so we have a comet here. I can tell you right now, this is the ion tail. This is the dust tail. So for the comet shown to the right, what direction is the sun? Okay, so it's actually this one. It shouldn't have faded out, sorry. The ion tail points in the direction of the sun. It has nothing to do with the orbit or direction of the comet. Yeah. So the solar wind is pushing away those electrically charged ions. Which direction is the comet actually moving, though? Because its orbit is not, of course, in the direction of the sun. Yep. So I see a lot of force. So we'll just say, yeah, the tail of dust and debris is left behind that moving comet. So I'm going to spend a minute to tell you guys about famous comets. The first one that I think most people have heard about, if you've ever heard of the name of a comet, is Halley's Comet. Some people say Halley's Comet. We don't actually know how he pronounced it. Astronomers tend to say Halley's Comet, so that's what I'm going to say. So comets before Sir Edmund Halley, who was the he was an English astronomer. He's the first person who figured out what comets really were. So people thought that they were some sort of vapor in the atmosphere. They didn't realize they were celestial bodies. But what people did think back in the day was, a comet is the sign of doom or something bad is happening. If one of these things is showing up in the sky, because they could be big, they can be incredibly bright, bright enough easily to be seen with the naked eye. You can have tails that go very long distances. That must be a bad omen, right? What Edmund Halley did was in 1705, he was calculating the orbits of famous comets that had been seen, in recent centuries. And he realized that there was a comet that was seen 1682, 1607, 1531, actually the same comet. And he was just because he was calculating the orbit of these, and he realized, okay, this must be the same body coming back. We actually now have gone back into the literature, and the first time humans have seen Halley's Comet was back in 240 BC. There's a record of Chinese astronomers seeing this comet. What he also then said, okay, so there's a period to this comet. It's something out there in the solar system. It's going to come back. He predicted that it was going to return in 1742. He died, unfortunately, before 1742, but they did see it that year. So then this is the comets are normally named after their discoverers. This is the only real exception to the rule, because if you're the first one to figure out how comets work, you get your most famous comet named after you. The reason it's kind of a famous one, so first of all, it's been seen, as I said, a lot of times in history. So 1066, like the Wikipedia page, by the way, for this comet's kind of amazing. You can see all these like historic documents where people painted the comet and things like that. This is probably the most famous one in antiquity. So in 1066 AD, William the Conqueror conquered England, and there was this terrible comet in the sky, which is, of course, showing that the King of England at the time is about to be deposed. They stitched it onto the Bayeux Tapestry, which is kind of the famous record of William the Conqueror. So if you ever go see the Bayeux Tapestry, you can see Halley's Comet on it. The second reason it's a famous comet is it's actually a very, very bright comet. When it comes by every 76 years or so, it is usually bright enough to be one of these very bright comets that even non-astronomers, you just go out and you'll see it. And there's usually a bit of hype because, of course, anything that we've seen over history is always very exciting. So this is, an astro photograph from 1910 from Wisconsin, USA, Yerkes Observatory. So it was kind of fun. I was like, well, I'll show you guys one of the previous ones. And then 1986, this was actually the first time we visited a comet. There was a flyby that the European Space Agency sent. And then you can see this is what Halley's Comet looked like from an actual mission. So, we have that coma forming, we have that dust tail, ion tail, things like that. But so this was its last time in. And I looked it up for you guys. Next time is July 2061, which is about 30 years from now. So, we're all going to be off doing other things in that time, but then you'll think back to this class and you'll be like, okay, my teacher told me that I was someday going to see this. And you're right now thinking, oh, I'm going to be so old then, who cares? But, may we all see Halley's Comet one more time. Another famous comet that is happening right now as we speak of, and I know some of you guys are interested in this because you asked me about it, is called 3L Atlas. So 3L Atlas is an interesting one worth discussing because it was discovered in July 2025 by Atlas, which is it's up on a mountain in Hawaii, an automatic sky survey looking for comets that could maybe hit the Earth or something like that. And when they calculated its orbit, they did confirm that it's the third ever detected interstellar object passing through the solar system. What do I mean by this? What I mean is, so here on the left, we have the orbit of this comet. And you can see it's coming in, it's going out. It's basically a straight line, slight change in orbit from passing through our solar system, but this is about as straight a shot as you get. There's no sign that this eccentric orbit is eventually going to come back and it's going to only stop at as far as the Oort cloud. So this has been very, very exciting. It's likely older than our solar system. They can kind of calculate the direction it came from. So it's coming from inside of our Milky Way. We think that it's, probably about 7 billion years old, could even be older than that. So billions of years older potentially than our own solar system. And what likely is its history is, so it did form, as whatever star, its parent host star formed in that solar system. But then after it formed, it was ejected from that initial solar system by either a giant planet there or a star. It's impossible to these days track it back to where we came from because stars in the Milky Way move pretty much. Nothing is where it originally was. The reason you might have heard about this is the first thing I have to say is no, it's not aliens. There's a certain astronomer at Harvard University. His name is Avi Loeb, and he's currently going on a media rampage. Basically, anybody who hears him, he's like, could be an alien spaceship. And then when you're like, no, all the evidence shows comets, he's like, I'm just asking questions. And so I was at Harvard before here, so I met Avi a couple times. And first of all, I will say, very smart guy, actually a good professor. I wouldn't put him in this class, but for graduate level classes, I'm told he's pretty good. But the second thing is he really likes attention. So, as some people do. And some people start to, just asking questions, and then they go off into what pseudo is basically pseudoscience. So if you talk to people who are actually in the community where you study comets, there's a general rule in science that extraordinary claims require extraordinary evidence. There is no evidence beyond Avi saying, but it could be an aliens, that this is actually that. All the evidence points to comets. I'll also say that Avi by this point is definitely just like ignoring evidence that is not convenient for his claims. So, I mean, I think the moral of the story for 3L Atlas is, we should always keep an open mind in science, but don't keep such an open mind that your brains fall out. I don't know if you've ever heard that expression, but I think it's very appropriate here. I mean, it is very, what are the odds that this exact comet was going to be coming through our solar system exactly this time? Yeah. Yes, but we have a very big universe. Turns out when you have a very big universe, you have all sorts of things out here. You've had how many comets that were flung out of our own solar system at early times? Like, there's got to be trillions of these floating around the solar system. It's just they're very hard to detect. We're only really technologically getting to the point where we're able to detect these things. So yeah, 3L Atlas is not aliens, but it is a very, very cool object. It's definitely a very old object. I think that's fair enough to say. But it's going to keep carrying its merry way. And, then we'll find another one, and then Avi will be like, oh, it could be aliens. So, now you know. Kuiper Belt. Kuiper Belt objects. So the Kuiper Belt objects are basically the ones that live beyond the planet Neptune. And the biggest example of them is the dwarf planet Pluto. So Kuiper Belt objects are different from asteroids, and this is because they're formed much further out. They're rock and ice in various mixtures, usually more dense than comets. So they're not quite comets, they're not quite asteroids, there's some sort of species in between. I should mention Kuiper Belt objects. They're named after Kuiper was a Dutch astronomer who first theorized that this region of space should exist. The composition of Kuiper Belt objects, you can see here, they are pretty low density. I mean, water ice is one, so very low density. They're not rocky. I think that's fair to say. I'll also point out that we have some dwarf planets here in this mix. Some of the Kuiper Belt objects can actually be quite respectably large. That makes sense because by the time you're getting out there, not much light, getting hard to see those things. So if you're much bigger, then it's easier to see. Eris is notable, by the way, because it's called that. Eris was the Roman god of strife, because it turns out Eris is bigger than Pluto. It's just further out. So once they discovered Eris, it's like, well, do we have more planets? Do we kick out Pluto? It was indeed the god of strife for poor Pluto. There's some pretty cool ones out there. So this is an example of a double object, Kuiper Belt. It kind of looks like a peanut. We know this from radar mapping technology, I believe. It's mainly rock and water ice, but the idea is that when it formed, you had two of these Kuiper Belt objects that they were rotating around each other, spiraled closer and closer, and eventually they touched. So they never quite collided, but they touched, and now they fused into one peanut object. So that's pretty cool. Otherwise, yeah, they're just kind of big hunks of, as I said, rocky ice. And we'll wrap up here with discussion of everybody's favorite dwarf planet, or, Pluto's a planet stuff, Pluto and its moon Charon. So the way we define planets, I think we've covered this at some point already, but as a reminder, you need three things to be a planet. The first is you have to orbit the sun. I think that makes sense as a criteria. The second is you have to be approximately spherical. And the third is you need to dominate your nearby orbit. So if you don't meet criteria 1, you're basically a large moon, because that means you're going around Jupiter, Saturn, or the Earth, or whatever. You also are not going to be number 3. If you don't meet criteria 3, you're a dwarf planet. In the case of Pluto, Pluto crosses the orbit of Neptune. So it is actually the closer than Neptune for a short period of its orbit. So that means it doesn't have its orbit cleared around it. It's not the biggest guy on his block. So that's not great. And then if you don't meet criteria 2, you're basically a big asteroid. I was also thinking about this. I think you also probably never pass number 3 as well. So The way this all happened was, so as I said, Eris was discovered, and then I think it was sometime in the 2000s, early 2000s, the International Astronomical Union are the people who decide what things are in astronomy. And it's a conference. It meets every couple of years, every 3 years or so, different place in the world. I actually know people who went to that one. They were like, yeah, it was pretty cool. We got to vote on Pluto. I was like, okay. The thing about it is, so at first, the committee that was sent to the room to discuss what it should be came back and they said, well, how about we just have like everything's a planet? So Pluto gets to be a planet, Eris gets to be a planet, all the dwarf planets. And people were actually very outraged by that because they were like, but how will school children learn the names of the planets? My answer to that is like, have you ever met kids? Like they'll learn the names because kids just really like stuff like that. So if they went back into the room, they came up with this definition. I think also at the end of the day, the thing to remember about definitions is humans really like to categorize things and make definitions for things. That doesn't necessarily make it a scientific thing. And my experience is usually science is more interesting when we talk about the physical properties of a thing and not how we define it, because that just kind of starts getting around in circles and is not actually as interesting. That's my personal opinion. But anyway, so we made up this category called dwarf planets, and then we ended up putting some things into that category. So they're big enough to be roundish for the most part, but they're still pretty small. All of them except Ceres are out in the Kuiper Belt and beyond. This is the Earth to scale. So you can see they're pretty small. Some have moons. I mean, other ones might have moons. We just can't really detect them. Their density is lower than the terrestrial planets. So if we're looking here at this density and water is one, showing you guys this earlier, most of the densities for these planets are very, very low compared to, say, Mercury and the Moon, which are actually rocky planets. Key characteristics of Pluto. So Pluto was first discovered in 1930 by an astronomer named Clyde Tombaugh in a Flagstaff Observatory in Arizona. And when they discovered it, the reason it also was classified immediately as a planet, first of all, they didn't know the Kuiper Belt existed. Secondly, they didn't know that Pluto had its moon Charon, which is actually a very significant size, you'll see in a minute, compared to Pluto. So they actually thought, based off the initial light curves and things like that, that it was bigger than Mercury. So it's like, okay. And then they discovered, oh, it's smaller. Oh, it has all these problems. Then they discovered Eris. Anyway, the rest is history. It's pretty far out there, 248 8-year period. Semi-major axis about 40 times further than our sun. This is the average for it because it is a very eccentric orbit. Rotation period about every 6 days. Very high orbital tilt. It's probably gone through some things in the early solar system. Known moons 5. So the biggest one is Charon. But when New Horizons flew by in 2015, which is the only mission that has ever visited Pluto, they saw 4 more as it flew by. So that's how we know the other moons exist. So Pluto and Charon are about the same size, I said earlier. So Pluto is 2,400 kilometers in diameter. There's a famous little fact that sometimes you read on the internet that Russia is bigger than Pluto. If you're thinking of a sense of scale, yeah, Russia's either really big or Pluto's very small. But Charon is 1,200 kilometers. So this is almost more a double planet setup than a see, is this little video going to work? No, it's not, unfortunately. Sorry. So they're also doubly tidal locked. So there has a center of orbit that's between the two, center of gravity for the system. So this would be the equivalent of we always see the same face for the moon. We've discussed that. Imagine if the Earth always showed the same face to the moon as well. That's what's happening in the Pluto-Charon system. Pluto's surface has very few craters. It's an old surface, but there's just not as many things that are impacting out there in the Kuiper Belt compared to in the outer solar system, where you just had a lot more stuff going through back in the day. Pluto has a heart because it loves us very much. It's called the Tombaugh Regio. Half of it's called the Sputnik Platinia, an old crater filled in what we think is a nitrogen glacier is what is causing the heart on Pluto. Pluto is also a very different surface to any other surface that we've really studied in detail. It has water ice mountains. So those are these features here. And the rocks on Titan are also water ice, to give you an idea. But so basically have these giant water ice mountains. You could ski on Pluto, is what somebody told me once. Assuming you could breathe and all that. But anyway. And then this is also, as I said, there's that glacier, the nitrogen glacier. It's a solid nitrogen glacier. So it's something you can't have on our own planet, but it's very cold out there, not very big. Can happen there. And we can see the glacier features going into this more rugged cratered terrain. Looking back from Pluto's atmosphere, it does have an atmosphere. So this was after New Horizons went past Pluto. It looked back and we got this picture. You could see the layers of the atmosphere very, very well here. Very low percentage compared to our own atmosphere or any other atmosphere, but it does exist. And I also think this is just artistically a very, very lovely shot. And then also there was a view of Charon, because they took the picture as it went. So it does not have a nitrogen glacier like that, but it does, I think, give you a more clear view of what that actual surface looks like. So very old surface. You have some scarping. There has been some geologic activity here, but for the most part, there's not a lot going on. There's definitely some huge crater here. I think Charon's also cool because I actually went to college with the guy who was in charge of the Charon data as it was coming in from New Horizons. So the way this works, so New Horizons is flying back past. It's flying very, very fast. They basically set it up because also the other thing to realize, by the time you're getting out there, the signals coming back to Earth are very, very weak. It's worse than a dial-up internet connection in terms of getting the data back to Earth because you're just so far away. Also, it takes many, many hours, right, by the time because of the light travel distance. So what they ended up doing was just setting up the probe to do all the data taking that it could do. And then it took almost a year to get all the images back from Pluto and Charon after it had initially passed. So it was actually very cool for me because my friend was then just posting on social media all these new Charon pictures for like a year because he's the first person who got to basically open them up, look at them, have some initial idea of the geologic stuff that's going on. This is one of those things that Steve, that was his name, looked at. Um, Finally, a bit of a recall knowledge. If nitrogen ice warms up at low pressures, what happens on Earth? Will it turn into a liquid or a gas? Yeah, so it's going to turn into a gas. It's going to sublimate, that word. So nitrogen will sublimate if it's closer to the sun. So that's why we do not have nitrogen glaciers on our planet, but it's sufficiently cold out at Pluto that this state does exist. So that's pretty cool in my book.